Hello, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development in Grasshopper. This video is going to be the first video in a small series of 3 videos where I'm going to teach you how to model dynamic simulation inside of Grasshopper mimicking continuous execution. And the first example that we're going to do in this mini series is going to be a really simple one, which is going to be taking a point in three-dimensional space, defining some kind of boundary, and then creating a simulation where for some starting velocity and some starting location, we're going to model that point moving in this boundary and bouncing off the boundaries of this region. Okay, so that's going to be a rectangle, a point, a vector, and then how this moves in three-dimensional space. You can see that this simulation is not actually perfect for the reasons that we will explain very soon, but it's going to be, the first one is going to be a warm-up to the other 2 videos, which will be modeling a pendulum and modeling the deformation of an elastic rope sagging under its own weight. So that's going to be the next 2 videos. All right. So, but this is going to be cool and fun because with this now we can model systems that dynamically change over time and that generate form. So that, for example, we can now bake this in three-dimensional space, and we can bake this and then use this as some kind of pattern or some kind of geometry that we use for a facade. I don't know. It's absolutely up to you. Okay. So let's get hands-on and perhaps like go to the whiteboard first and then break down this problem, how we're going to tackle it. Okay, let's get hands-on. All right, so let's start with the fun. So the first example that we're going to do is going to be super simple. We're going to imagine we have some kind of region that is defined by a boundary. And to make things easy, we're just going to choose a rectangle. And then we're going to start with a determined location. So we're going to start with a starting point, and we're also going to define some kind of starting vector, which is going to define the initial direction of motion. And what we're trying to do with this exercise is that we're trying to create a simulation. We're going to try to create a simulation that is going to make this point move in the direction of the vector with the speed of the vector. So every step, we're going to move an amount that is going to equal the length of that vector in that direction. And then as the simulation evolves, as we hit the regions, we're going to start bouncing back, and we're going to create something of the kind that is going to just be moving around and bouncing off the region boundaries, etc., and create this evolving pattern of I don't know. I don't know what that is, but it's going to create this kind of simulation. Okay, it's going to be super easy. You're going to see. So let's take a look at how to do that in Grasshopper. So I have gone ahead and created a C# script component that has a few inputs already. So it has a starting point, a starting velocity. So this is going to be a vector, that vector that defines direction and defines magnitude as how fast this point is going to move every iteration. And I've also defined width and height as a simple way of defining the boundaries of the region, right? And we're going to start very simple. So I'm going to make sure that I don't forget to specify the types of the inputs. So the starting point is going to be a point 3D. The start velocity is going to be a vector 3D, and width and height are just going to be numbers with decimal part. So you can't see it on my screen, it's flowing on my other screen, but that's going to be a double, and this is going to be also a double. All right. And we're going to start super easy. What we're going to do is, first of all, just for the sake of visual, we don't really need this, but just for visual reference, I'm going to create a rectangle that is going to live within those 2 boundaries. So I'm going to define a rectangle in Rhino Common that I'm going to call, for example, the boundary. And this is going to be a new rectangle 3D. Actually, rectangles are rectangle 3D. That's the name of the class. And then as I open, you can see that it asks me for a base plane. We're going to simplify this example, so we're not really going to account for the possibility of simulating this in 3 dimensions. And in order to do it well, we should actually take the point and project it into that plane, etc. We're going to oversimplify it a little bit, but You, the viewer, you're welcome to extend this example and make it better, more resilient, and more all-road in the future if you wish so. So I'm going to keep it easy and just going to just choose the world XY plane for this rectangle. And then you can see that I have a constructor that gives me the width and the height. So I'm going to plug those right away. Okay. And for the sake of visual representation, I had two outputs on the component right now, R and P. So I'm going to use R for the rectangle. So that's going to be boundary. Okay. And as we've been doing in the previous example, so this is going to be all the algorithms that I'm going to write, and then the output is the boundary. If I do that, and nothing happens because I don't really have values associated here. So let me plug in a few numbers here. So this is going to be the width, and now this is going to be the height. And you can see that I got this rectangle that is really large in space. And if I plug in a panel, you can see that I have a rectangle, which is actually more like a square at this point, but whatever. So beautiful. Let me take a second to create a couple of points and vectors that I'm going to plug in here in the input. So what I have done is I have gone ahead and in Rhino, I have created 2 points that I have brought into Grasshopper by referencing them, the one on the left and the one on the right. Okay. And the one on the left is the one that I'm going to be using as a starting point. And the one on the right is going to be just a secondary point that I'm using to define the velocity, which I'm defining as a vector between the first point and the second point. So that I'm also visualizing here. So this point is actually useless, but I'm using it to just easily to have like a drag of like, how to set up the initial speed rather than having two sliders, which sometimes is a little not so nice, all right? So but you could choose like a vector that you create with your sliders, etc., as a way of doing this. Beautiful. So now I have a starting point. So I have the rectangle, I have the starting point, and I have a starting velocity for the point to move. At this point, we are in a very similar position to the example that we did in the previous video on this series, where we just took a point and we made it move along a vector. So we're going to try that, okay? So if you remember, in the previous video, I explained that in this area of the C# script component, because we are inside of a class, I can just add more members to that class. What that means is that I can create variables that live outside of the main run script function, and those variables, whichever values I give them, are going to be persistent, are going to survive over different iterations, different executions of the component. So what I can do here is I can say, first of all, I'm going to create a point 3D that I'm going to call location. And this is the variable that is going to store the position of the moving point at any point in my simulation, right? Let's call these frames, for example, at any iteration of my simulation. And I'm going to start it with some random values. So for example, I'm going to start it with unset, okay? And then we also discussed how it's typically useful to have like a reset flag so that you can signal to the component that you want to start with a particular, you can start when you press a button or when you signal that flag so that things reset and then we can kick off the simulation. So I'm going to go ahead and add here another input. I'm going to call this reset. I'm going to call this reset and I'm going to right click and make sure that this is of the type Boolean. All right. And I'm also going to plug in here a Boolean button. All right. And then so this on, reset, not reset, etc., etc. So what's great about this is that now what I can do is I can say in my algorithms, I can start by saying if reset equals true, or we know we can short this. If that is true, what I can do is I can make sure that in this particular iteration, I take whatever the point location has as a value and I override it with my starting point. So I'm going to say location needs to be equal now to my starting point, but only when I reset. After that, location should get whatever value that is coming out of the simulation. So at this point, this is working and I don't get any errors. All right, so that's great. So here I am drawing my boundary. Okay, but again, I only need this basically for visual flavor. So I'm going to just push this all the way to the end. And then what I'm going to do here is that if I'm not resetting, okay, what I should do is that I should take the point and then make sure that I move that point with the vector that defines velocity. So we saw that in the previous example. So I'm going to say update location of moving point with velocity. So I'm going to say location, not starting point, because starting point is always going to be the same, but location is the one that needs to change. Location needs to change at a rate defined by starting velocity. Okay. All right. So let's see if that works for the time being. Oh, and I forgot that over P, the output, I want to be outputting the value of location because this is the point that is going to change over time. So I'm going to reset this and you can see that I already, only by pressing the button and releasing it, I've already executed like 2 instances of my simulation. And if I were to put here like a trigger component that resets every 200 milliseconds, you can see how the point is starting to move at a rate defined by this velocity. And if I press the button again, you can see, can you notice the slight difference of like how I press and then it's already 2 steps ahead? I'm going to modify this and I'm going to say, if I'm pressing reset, then make sure that you set new values for all these persistent values and you don't execute anything else. So if reset is on, just don't execute any of the remaining code. All right. So that would save me one execution of this. It's just that also because I'm stopping the component, I'm not getting the rectangle, but that's fine. Okay. Beautiful. So this is working. Okay. But now how can I make the point bounce over the boundary of the rectangle? Well, there's a couple ways I can do that. So for example, the idea here is that when I know what I would need to do is I would need to do something whenever I know that the location of my point is beyond the width of the rectangle. So what I would need to do here is I can say if location dot x, so that is the location of the x location of my point. If this is greater than either width as a value, or if my situation was a bit more complex, what I could do is I could have created this earlier, all right? And I could say if the location of x is greater than boundary dot width, so that could be another situation. Or if let's just keep it like that, all right? If this is greater than that, then I would need to do something. What is it that I need to do? So for example, right now, I'm just going to print a message out of bounds. All right. I'm going to execute this. I'm going to put here a panel. I'm going to run my simulation and I'm going to restart it and then it's going. And you can see it's out of bounds. It's out of bounds. So what I need to do now is I need to make sure that if I am out of bounds, what I need to do is I need to change the direction of the velocity. If the velocity is pointing to the right, then what I need to do is I need to make sure that it points to the left. What that means in geometric terms is taking whatever the value of the x coordinate of the vector is and making it negative, correct? So you might be inclined to say, well, if this is true, then what I need to do is I need to say start velocity dot x is going to be equal to minus start velocity dot x. Okay? So I take the velocity and I flip it. This could be a good intuition, but let's see what's going to happen. This is not really going to do anything because if you think about it, start velocity is a value that is always coming from the outside. So the component is always taking the value of start velocity, which is given by Grasshopper, is whatever this is, right? And by the time this executes, start velocity always has the input value. And if I change this, and if this goes, if the point goes out of bound, yeah, well, I'm flipping the x coordinate of the input velocity, but I'm not using it anywhere else in the code. I've already used the one that doesn't have the flipped value. And because that's the case, and because start velocity on the next iteration is going to go back to whatever value is coming from the input, this will not work. So what I need to do is I need to make sure that I have some kind of more persistent value of the velocity, which I can use constantly and that I can change. And if I make changes, those changes stay for the next iteration of my simulation. So what does that mean? What that means is that when I start the simulation, I need to create a persistent point that I can change over time. But I also need to create a, for example, vector 3D current velocity, okay? Which I also can start as unset. And then what I can do is when I reset my simulation, what I say is current velocity needs to be equal to the starting value. All right. And then in my simulation, instead of using a starting velocity, I use current velocity, the velocity that I'm working with. But whenever I need to make changes to it, I make changes to current velocity so that on the next iteration, I still maintain the value of this vector that has been changed, that has the x coordinate has flipped for the next iteration. So let me run this for you. So I'm going to reset my simulation and I'm going to hit execute. And you're going to see that now, boom, it just went ahead and it bounced it off from the X coordinate. And now it goes infinitely to let me move this a little bit this way. So I'm going to reset this again and it's going that way and it bounces off and then it goes that, but it doesn't bounce off this from this other boundary. Why doesn't it? Well, because I need to add a little bit of more of code. So right now, it's only going out of bounds if the x location is greater than the width. But we can add here another, or if location x is smaller than 0, so that would be this boundary here, then also flip the direction of the velocity. So for example, I'm going to reset, I'm going to kickstart this, it's going that way, it's going to go that way, and then it's going to keep bouncing between x width and x0. All right, beautiful. That's great. But now, of course, we need to make it bounce also from the y equals 0 and y equals the height. So that just only takes a little bit of extra code to say here if location.y is greater than boundary.height or location.y is smaller than 0, then flip the y coordinate of current velocity. All right, current velocity dot y equals minus current velocity dot y. Beautiful. Shall we try this? Let's try it. I reset and then we go ahead, bounce, we bounce, we bounce. Can we make this a little faster? Let's do it a little faster. Ooh. All right. Okay, this looks like fun. All right. Now, maybe something that I may want to do is I may want to turn this into some kind of visualization. So I may want to be able to see the footprint of this point moving and bouncing across the boundaries, right? So maybe what I can do is like every time I move, what I can have is some kind of permanent polyline so that every time I move the point, I add another step to that polyline, and then I can see the progress of the point over time. Okay, let's do that. So I'm going to add another output here that I'm going to call T. That's going to be the trace. I'm going to call this the trace. And I'm going to add here a permanent polyline. So I'm going to add here a polyline that I'm going to call the trace, and I'm going to just initialize a new polyline. It's going to be an empty one. All right. And I'm also going to do this whenever we reset. We want to make sure that the polyline is blank. It has nothing on it. So I'm going to say here trace. I could do trace clear to just like empty it from, or I can just say, well, let's just make this a new polyline. All right. Before I forget, I'm also going to output it here. So that's going to be the trace. Okay. And then the only thing that I need to do is I'm going to add here bounds of boundaries. And here add current location to the footprint polyline, if you will. So what I can do here is to the trace, which is a polyline that I started empty, I can every frame I can add a new point. So that's I can add XYZ, or I can add a new point that I need, and I know that this is going to be location. All right, and I'm going to output this here. All right, you excited? Let's try this out. So I'm going to reset and then poo, poo, poo. All right, that's kind of cool. I'm going to, all right. That is actually kind of cool. I like it. Now, just for the sake of visual output as well, I'm going to output the vector, the velocity, so that we can see how the velocity is changing over time. So I'm going to add here another output that is going to be V, and I'm going to output here over V, I'm going to output the current velocity. All right. And I'm going to use a vector visualization to anchor on the point to visualize that vector. Sorry, to visualize this vector here. Okay. So I'm going to run this, and then you can see I have this, and I have the point that is moving. And I'm going to move this perhaps here. I'm going to reset it again. I have the point that is moving, and I have the vector that is showing the changing velocity over time, etc., etc. So, hooray! This looks cool to me. No, isn't this cool? You like it? All right. As you may have noticed, because I'm taking a few shortcuts, something that is happening is that the point is actually not the point is actually not stopping exactly at the boundary, and when it bounces off, from farther down. That is because if I have a boundary here, and my point at any iteration is like this, is right here, but the vector is longer, then on the next, like this, the velocity vector, then on the next iteration, that point is going to be somewhere here. And then at that point is when we flip the vector, and then in the next iteration, it's going to end up somewhere here. So there are ways we could do more calculations to say, well, when the point went off from the boundary, let's calculate how far off it went, and then let's subtract that from the location of the point, so that at that instance, so if we were here, let's just calculate how much this was and how much this was, and then let's roll the point back here, and then let's flip the velocity now. Okay, but that I am going to leave up to you, the viewer, to do as an exercise to improve this. And if you actually make it happen, I will be more than welcome to invite you to put a link on the comments of this video to your exercise and to share with the community, etc., etc. All right, with this, I think we are in a good position. This is what I wanted to get with this example. So this was the end of the first video in this three-part series where we're going to be doing dynamic simulation components. I think what we're going to do in the next video is that I'm going to teach you how to model a system that has gravity and spring forces. Like for example, we're going to model a pendulum that is going to be oscillating around an anchor point or something like that. Okay, so thank you very much for watching this video. You may want to show some gratitude, liking the video, subscribing to the channel, etc., etc., or not. That's perfectly fine as well. And see you on the next video. All right, let's model some pendulum. It's going to be a lot of fun. Thank you. Bye.